Look at the sheer volume of space between solar systems. This immense scale acts as a physical barrier that keeps humanity confined to its own corner of the universe. Our closest neighbor, the Andromeda Galaxy, sits 2.5 million light-years away. This chart compares how long it would take us to reach it. At 28,000 kilometers per hour, a standard spacecraft would spend 94.5 billion years in transit. Traveling at the speed of light cuts that down to 2.5 million years, a duration still far exceeding a human lifespan. Science fiction often bypasses these numbers by placing a theoretical wormhole near a local landmark, like Saturn. These shortcuts are rooted in the work of Albert Einstein, who provided the mathematical framework for how the universe is structured. Reaching another galaxy requires us to treat space-time as a system of mathematical rules that can be bypassed, rather than a physical distance that must be crossed. Einstein's field equations describe exactly how matter and energy interact with the fabric of reality. They show that space is not a void, but a pliable, three-dimensional mesh called space-time. Massive objects like stars and planets warp the mesh downward, creating the effect we experience as gravity. Travel becomes instantaneous by folding the entire grid through a fourth dimension, bringing two distant points into immediate contact. Once the layers are stacked, a bridge can be established between them. This tunnel is the Einstein-Rosen bridge. Because we live in 3 dimensions, this bridge would appear to an observer as a spherical orb reflecting the light of its destination. While the mathematics allow space to fold, tearing the tunnel open requires a force capable of permanently deforming the fabric of spacetime. Physicist Carl Schwarzschild calculated that a singularity, a point of infinite density, possesses the gravitational power required to punch through folded space. A black hole acts as the engine for this shortcut, pulling light and matter into the mouth of the tunnel. However, if the exit on the other side is also a black hole, anything entering the tunnel is trapped forever. To work as a shortcut, the tunnel needs an exit strategy. This requires a third component, a white hole. Mathematically, this is the time-reversed opposite of a black hole. While a black hole allows no escape, a white hole allows no entry. Its event horizon acts as a boundary that violently expels matter and light into the surrounding universe. In 2006, satellites recorded an event known as GRB 060614, a massive burst of white light that occurred without the presence of a collapsing star. Scientists hypothesized this could be a rare observation of a white hole in action. A survivable shortcut depends on this precise alignment: a black hole to pull matter into the tunnel, and a white hole to ensure it can only move outward on the other side. At this stage, cosmic wormholes and white holes are theoretical solutions to complex equations. But black holes were also considered mathematical curiosities for a century, before they were finally observed and photographed. Scientists are already testing the logic of these bridges using other forces. In 2015, a team engineered a laboratory-scale wormhole, not for gravity, but for magnetism. By using superconducting materials, they created an invisible spatial gap between a magnet's north and south poles. The magnetic field enters one sphere and reappears out of a completely separate sphere, effectively bypassing the space in between. Other mathematical solutions exist for interstellar travel, like the 1994 Alcubierre drive. This warp drive moves a ship by contracting spacetime in front of it and expanding the mesh behind it, allowing the vessel to cover distance without technically breaking the speed of light. Physical distance remains an obstacle for now, but the mathematical framework for a shortcut already exists. We are currently limited only by our ability to engineer what the equations say is possible.